highly recommend going.
Okay, let's get started. This is kind of an interesting workaround to try to get this to work. I am not sure if it's going to record the entire presentation today because I have to record it to the flash drive. So hopefully it will, but if not, sorry. B drive's not accessible. Computers are all messed up. Okay, so today we're going to do a lot of math in symbolic form. And I know you guys like to just jump right to putting numbers and things, but I need you to work with me in doing things in symbolic form so that you can understand the process. So as we're working through these differential equations, partial differentials, it's important that you write down the steps involved and make sure that you follow them. Okay, so the notes are up online, and I had to do it in two separate files. One is the lecture with the PowerPoint, and the other one is the examples from the lecture, because I couldn't combine PowerPoints. I didn't have access to Adobe due to computer issues. So, you can look at the notes later and follow along now, but I would highly recommend that you try to write down the steps and follow along so you can understand the process. Okay, so the homework is due on the 17th. That's next Tuesday, and the homework is going to just be on refrigeration and heat pump cycles. The next homework will just be on this partial differential stuff that we're doing. So we're a little bit a lecture ahead as far as homework is concerned, but I think that's not necessarily a bad thing. So today's lecture will be on the next homework, but don't let that deter you from finishing quickly the old homework. It should actually be an advantage to you because you should already be halfway through it. Okay. So chapter 12 is all about the property relations that we use to determine changes in enthalpy or entropy or specific volume or pressure or temperature based on other property values. And because those properties are all sort of dependent on one another but independent of one another also, we have to develop these equations that allow us to look at the property and how it changes when we hold other things steady. So as we do these partial differentials, that's kind of what we're doing in mathematical form, is we're changing some of the variables while we're holding other things steady. So that allows us to analyze and look and see trends. As our process undergoes some specific changes, then we can determine how that will affect pressure or how that will affect enthalpy, things like that. So let's just first talk about derivatives. So what is a derivative? In its most basic physical form, the derivative is a slope of a line. And when you're looking at a derivative, it's a change in something over a change in something else. So in two-dimensional forms, there's just two variables, an x and a y, and you're looking at change in x over change in y. And where it meets with this function line at that very point, that is where you are finding the slope. Maybe I can't write on the screen today. I don't know. So you're finding the slope of the line at this particular point. Can you see? I do. No. What about you, the mouse? Can you see the mouse? Okay. So you're finding the slope of the line at this particular point. So this derivative, or df dx, is equal to the limit as x approaches 0. So as we're incrementally decreasing the distance between points of this change in f over change in x. So we can rewrite it as it's the function at x plus delta x minus the function at x divided by delta x. So that's how you find this rise over run. So it's this change in function over some change in x. And when this derivative is equal to 0, it means that our line is flat. So that can either be a point of minimal, of the minimum of the function, or it can be the maximum of the function. So if you're looking at a curve that's like this, it would either be at the very tip of the curve or at the bottom of the curve. So a maximum or a minimum. And it can be a relative max. Do you have a pen? Thank you. Or a relative min. Don't let me steal it. So there may be more than one maximum in your function and more than one minimum, but you're finding the derivative for the minimum at that point. It's a localized maximum or a localized minimum. So when you're looking at a function That's just changing based on a single variable. So this function of x is just dependent on x. Then when you take the derivative, it's the total derivative, because only one variable is changing and you can define it at every point. A partial derivative happens when we're working in like a three-dimensional space, because now we have a function that's dependent on more than one variable. In this case, we're looking at functions, or in this class today, we're looking at functions that are dependent on two variables at a time. So in order to take a partial derivative, you look at the function and you hold one of those variables constant, let's say x, and you change y. Then you hold y constant and you change x. So the partial derivative allows you to look at the total effect of the change of both of these variables, but you have to look at them one at a time, is essentially what we're doing. So when x and y are independent of one another, we can have a total derivative that's the same thing as a partial derivative. So if x and y are not dependent at all on each other, then a partial derivative is the same thing as the total derivative. But when x and y are dependent on one another, so changing x will also affect y and z, then the total derivative is the sum of the two partial derivatives. So let's look at how this comes about, and I'll have to write it on the board instead of on here, because I think I don't know where all my tools went. How do I get my ink back? There we go. Okay, I figured it out. Erase and write. I can do this. Okay, so if we have some equation or function delta z that's dependent on x and y, we can rewrite that as a change in z is equal to z when we're at x plus delta x and y plus delta y minus z when we're at x and y. So if we change both x and both y by some incremental amount, that's how we find how much we've changed z. Okay, so to derive this partial differential, we're going to add something and subtract something to this equation. So we're going to add z of x, comma, y plus delta y, and then we're just going to subtract z of x, y plus delta y. So essentially we've added 0 to the equation. But we do this so that we can move the terms around and manipulate. So we're going to have a delta z is equal to z of x plus delta x, y plus delta y, minus z of x and y plus delta y. Those are z's. And then we're just going to divide this by delta x and multiply it by delta x. So essentially we're multiplying by 1. That's okay. That's our first term. Then our second term is z of x, y plus delta y minus z of x, y. And then we're going to multiply that one by delta y and divide that one by delta y. Okay, so we've added and subtracted the same thing, and then we've multiplied and divided each of these individual terms by 1, essentially. Okay, so this is just mathematical manipulation so that we can cancel things out and get what we want. Yes, do you have a question?
No, I'm just
Okay.
kind of...
Okay, so then we can reduce this by getting rid of this delta y here and this delta y here. It comes down to x plus delta x, y, minus z of x, y, delta x over delta x, plus z of x, y plus delta y, minus z of x, y, times delta y over delta y. So z of this function and z of this function are Actually, the brackets are outside there. Is the same thing as this partial derivative here. So this term is this, and this term is this. So this del z del x is all of this over delta x, and this del z del y is all of this over delta y. And there's a cleaner copy in the text or in the notes if you have a hard time following the red scribbles. So this total differential of a dependent variable is written in terms now of the partial derivatives with respect to independent variables. Okay, so we're able to separate out the dependency by allowing them to change with one variable and holding the other variable constant. Okay, so let's do an example of this so we can kind of see a little bit better how it works with the ideal gas equation. So if we are to rewrite the function for an ideal gas, dz equals del zx with holding y constant dx plus del zy holding x constant dy. This is just the basic equation for partial derivatives. We can rewrite it in terms of P, T, and V. So now we're saying that the pressure is changing and we're going to hold the volume constant and change pressure with temperature. Then we're going to hold the temperature constant and change pressure with volume. Okay, so for an ideal gas, P is equal to RT over V, where R is a constant, and T and V are allowed to vary. Okay, but in this case, V is held constant, and in this case, T is held constant. So as we put the equation in for P, when we take the derivative of this part, we allow T to vary, and this part we allow V to vary. Okay, so dP is equal to the partial derivative with respect to temperature of RT over V, while we hold V constant, dT, plus the partial derivative with respect to volume, RT over V, dV, as we hold T constant. So if we take the derivative of each of these, it's R dt over V minus RT dV over V squared. Okay, so this is the equation. And if we are using this in practice, we have to take our temperature difference. So we're going to do an example where we go from 300 to 302 or 300 to 400 K. So that's going to be our dt. And then we'll use some constant average value for the volume. Similarly, we'll use a dV, which is the change in volume, and a constant average volume, and a constant average temperature. Okay, so we're going to look at using this equation and how accurate it is compared to just using the ideal gas law at the outset to see if it can work for us in a good way or a positive way, and over what temperature intervals it's consistent and accurate. Okay, so let's look at the first case where T1 is 300 Kelvin, T2 is 302 Kelvin, V1 is 0.86, and V2 is 0.87. So we're going to calculate how the pressure will change over that interval, and then we'll compare it to the actual value and see how much percent error we have with that. Okay, so T1 is 300, T2 is 302, V1 is 0.86, V2 is 0.868. No, can't be the same. 0.87 meters cubed per kilogram. Okay, so let's plug it in. dP is equal to R, which is 0.2870 kilojoules per kilogram Kelvin. We can take that out of the equation and just put it up front. Multiplied by dt. So what is dt in this case? 2. Yeah, 2 Kelvin. Divided by V. And so V, we're going to say V average is equal to 0.86 plus 0.87 over 2, which is 0.85 meters cubed per kilogram, so 0.85 meters cubed per kilogram, minus T, average, which will be 301 Kelvin, times dV, which is what? What's our change in volume? 0.01 meters cubed per kilogram, divided by V squared, and again it's that average, V, 0.85 meters cubed per kilogram squared. Yes?
Should I do 0.865?
Yeah. 865. Yeah, it wouldn't be less than the 2. Yeah. Okay.
And then the 301 is the average you're doing?
301 is the average, right? And I did that one correct, didn't I? 0.865. 865. Okay, so when we calculate that, we find dP is equal to negative 0.491 kilopascals. How would we find the actual dP?
Wait, what's it say? Negative?
Well, the eraser is so huge that I can't erase very well, but negative 0.491. That's 4. Now, dP is equal to negative 0.491 kilopascals. Okay, so how would I find the actual change in pressure?
Use centimeter each other? I don't know.
Just with the ideal gas law, right? So P is equal to RT over V. So R1 T1 over V1 is equal to 100.116 kilopascals. R2 T2 over V2 is equal to 88.307 kilopascals. So, is that right? That's the next problem. Uh, 99.625. So our delta P ends up being negative 0.491 kilopascals. So our percent error in this case is 0. Because we can assume that over a small temperature interval, the relationship between pressure and temperature and specific volume has a linear component to it. Okay, so now let's see what happens if we use a larger temperature interval, so 300 Kelvin, to now we're going to use 400 Kelvin. And we're assuming V1 is equal to 0.86 again, meters cubed per kilogram, and V2 is 1.3 meters cubed per kilogram. So we find our T average is equal to 350 Kelvin. Our delta T is equal to 100 Kelvin. V average is equal to 1.08 meters cubed per kilogram. And delta V is equal to 0.44 meters cubed per kilogram. So we can do the same thing where dP is equal to R, 0.2870 kilojoules per kilogram Kelvin, multiplied by our delta T, which now is 100 Kelvin, over our V average, which is 1.08 meters cubed per kilogram, minus our T average, which is 350 K, multiplied by our delta V, which is 0.44 meters cubed per kilogram, divided by V average squared, which is 0. Oh no, not 0. Ah! 0. My brain. Not 0. 1.08 meters cubed per kilogram, and that is a V squared. So we calculate dP is equal to negative 11.319 kilopascals. And if we use, again, the ideal gas equation, we can calculate P1 is equal to 100.116 kilopascals. P2 is equal to 88.307 kilopascals. So our delta P in actuality is negative 11.808 kilopascals. So our percent error is about 4.14%. Okay, so again, this is because we're approximating the slope and assuming that it's constant over that whole interval, which in actuality is not, it's slightly curved. But we still just get a 4.14% error. For the ideal gas equation, it seems silly to do this because we have actual equations that are more accurate. But this is just an example of how you would use the partial derivatives to solve for unknown property values. If you wanted to know the change in pressure, you could take the partial derivative of an equation, and if it's, you know, if temperature and specific volume are changing, or enthalpy and entropy, whatever values you know or can calculate or measure, usually you can't measure entropy, then you can find that change and get a pretty good ballpark answer for the actual value.
Is there one way that's particularly better?
Oh yeah, using the ideal gas equation. But
Well, no, I mean like more like what you want it to be. Like is it supposed to be closer to negative 12 or closer to negative 11? Like,
supposed to be, well, if it's an ideal gas, it's an actual ideal gas, then it's going to follow very closely to the ideal gas equation. So ideal gas is easy because we have a known equation that works very well for ideal gases. When we start dealing with real gases, where the equation breaks down a little bit, then using these property relations actually helps us to find a better fit than if we were to just assume it was an ideal gas and calculate it that way. Does that make sense? Do you have a question?
Yeah, partial differentials are my strong suit. So you solve for P, and then you differentiated that twice, once with respect to T and then once with respect to V.
Yes.
And added the differential statement.
Yes.
Okay.
Yeah, and so if you had a third variable, then you have to do like holding two constant, changing one, so you end up with more terms. So the more variables you add, the more terms you have. We're only doing 2 in this class. But. Okay, so this partial differential form, it ends up being quite useful to us to derive other property relations. And so we're going to go through that, but this is kind of where it comes from. That if we take this equation, again, that's just the basic form for the partial differential equation of a function dependent on 2 variables, we can say that this is m and this is n, just for simplification. Now we're going to take the partial differential of m and the partial differential of n with respect to the opposite variables. So in this case it was z with respect to x, holding y constant. Now we're going to take this with respect to y and hold x constant. So it's like taking the partial differential a second time. And when we do that, we get 2 values. When we do m with x and n with y, we get 2 values that are exactly the same to one another. So therefore, we can conclude that the partial differential of m with respect to y, holding x constant, is equal to the partial differential of n with respect to x, holding y constant. You may just have to take that and believe it as fact. Because now we go on and we use that to derive some other very, very useful equations in another way. So this is true. You have to believe it. We're going to use it later, but we have to derive some other relationships first. So let's say that we have this function z, and so you can imagine that there's any function like z plus xy minus y squared is equal to 0, right? So we could take the derivative of z with respect to x and y, or we could take the derivative of x with respect to y and z. It just depends on how how we rearrange the equation, because these three variables are working together to give you a solution set in 3D space, right? So x, y, and z are all changing to one another. We can look at from the z reference frame, or we can look at from the x reference frame, or the y reference frame. Any of those are accurate, just depends on which one we want to evaluate. More math. It's great. So we're going to do that. So now we're going to say, okay, I want the function in terms of x instead of in terms of z, and I'm going to take the partial of x with respect to y, holding z constant, and the partial of x with respect to z, holding y constant. It's the exact same thing that we did before, but now we're just looking at it from a different reference frame. So we found some value for dx, or some equation or relationship for dx. We're going to plug that back in here to this equation. So when we plug that in here and rearrange in terms of dy and dz, we get this and this. Okay, if we look at the solution set of the entire space, the only way that this can be equal to this is if the value in brackets is equal to 0. So that means this has to be equal to 0 and this has to be equal to 0 in order for this times dy to be equal to that times dz. That 0 is the only possible solution for those sets of equations. Again, just believe it's true. You don't have to prove it. Which means that if we're looking at this term and it is equal to 0, then we can rearrange and say, okay, if this is equal to 0, this plus this is equal to 0, then this has to be equal to negative of this, right? So this equals negative of that. Which means that we could also divide this equation by dz dy, or multiply by dy dz here, and then we just have a negative 1 left over on this side. So if we take this and divide through by it, that's the same thing as multiplying by the reciprocal. This is called the cyclic relationship. So if dz dx, holding y constant, multiplied by dx dz, del x del y, holding z constant, and del y del z, holding x constant, is equal to negative 1. So that's true for any partial differential equation in terms of those three variables, x, y, and z, a, b, c, d, e, f, whatever it is. That if you multiply the three partials together, you'll get a negative 1. It's awesome. Math is awesome. Okay, so then for this bracket, the only way that this can be equal to 0 is if this is equal to 1, which shows us that in reciprocity, that del z del x is the same as 1 over del z del x. Or that, no, it's not the same. That you can take the reciprocal of the partial derivative and it's equal to 1 over the partial derivative. Okay, so just like a fraction, reciprocity holds true. We should have proved this one first before we did this one, but, you know, you're out of order. Okay, so let's do some examples of equations. And actually, this is my older version of my PowerPoint because my V drive stopped letting me have access to it yesterday. So I don't have the equations written up here, and I only have one of them written down in my book, so we're just doing one. So let's say we have some equation, z plus xy minus 2y squared is equal to 0. I want you to try to find dz is equal to del z del z del x holding y constant dx plus del z del y holding x constant dy. Okay, so see if you can find these two terms from that equation.
So
that a plus?
Which one? This one?
No.
This? Yes, that's a plus.
Yeah, okay.
So you figure out how to make the eraser smaller. Better not miss this stuff. Can you change colors though? Woohoo! You already done, Blake?
I'm confused.
Okay, what would be the first step?
I've never been taught this way. What's up with the little y on the bottom?
That means I'm holding y constant. Partial derivative.
Okay.
So z is varying with x, but not with y. So when you look at the equation, so first step you would have to do is you'd have to solve this equation in terms of z. So z is equal to what?
Put it all to the right.
Yeah. So what would that be?
2y squared minus xy.
Minus xy, right? So if we want to take the partial derivative of z with respect to x, what would be the derivative of y squared with respect to x? What's the derivative? So if we're holding y constant, what is y in this equation? Y is not 0. What is y? Some constant, right? What's the derivative of constant? 0. So then what's the derivative of negative xy? Holding y constant.
Yeah, the derivative.
Negative y. So del z del x holding y constant is negative y.
So,
then-
so with the little y on the bottom, it's saying your answer has to have a y in it?
Not necessarily. It's just saying that you just treat y as a constant. So you don't have to worry about the derivative of y in this particular case. You're only looking at x. So if the equation were 2y squared minus x, what would the derivative of that be?
Which one are we doing?
This one, still.
With respect to x, it would be -1.
Yeah, it would just be negative 1. So there's no y in this equation, right?
Okay, that's what I'm confused
Okay. So now we do del z with respect to y holding x constant. So let's look at this equation again. What's the derivative of 2y squared? Or y? What's the derivative of negative xy? Negative x. So the answer is dz is equal to negative y dx plus 4y minus x dy. Boom. Math is awesome. Okay, any other questions on this?
So,
Just too dumbfounded to even ask a question.
oh yeah, but so, to clarify,
Yes,
so the partial z over partial x with the little y,
yes,
that's the same thing as saying partial z over partial x?
essentially.
Okay, that's what I was confused about. I've never put a y there.
That's just so we know that y is being held constant. That's the
Okay.
notation we're using in this class. So if in math, maybe you don't have that, but
Do we not do anything with the dx or the dy?
they're just there. So dz is equal to negative y times the change in x plus 4y minus x times the change in y. So again, this is used if we had, let's say z was entropy and x and y were temperature and enthalpy. then if we could measure or somehow calculate the change in enthalpy or the change in temperature, and then we know like initial and final temperatures or average temperatures, then we can calculate what will happen to our change in Z, whatever I said Z was, I forget already. Entropy? Entropy, yeah. So this is a way for us to look at how changes in other property values are going to affect some other property value. And because we're using partial differentials and we're assuming that it's linear over an interval, it's not going to be exact. But in some cases, that's the only way that we can calculate property values, like entropy, without having to measure at every single little interval along the way. Okay, so that brings us to the Maxwell relations. Hopefully you remember the first and second Gibbs equations. You may not have them memorized, but we have used them a lot, particularly when calculating entropy for an ideal gas. There's different forms of these equations that are in chapter 7. So the first and second Gibbs equation tell us how we can calculate a change in internal energy or a change in enthalpy based on entropy, pressure, specific volume, and temperature. Now we can also derive, and I'm not going to go through that derivation, it's in your book for lack of time, the third and fourth Gibbs equations, which talk about the change in the Helmholtz function, which is it's not an actual property, it's just something that comes up often when we're looking at some of these property relations, and the Gibbs function, same thing. So these again are based on changes in temperature, changes in specific volume, changes in pressure, and then some other known quantities or values. So we're going to take these four equations and we're going to apply this concept again. So if you notice, these are in the form of similar to what we saw before, that dz is equal to m dx plus n dy. And then we said that the partial of m with respect to y holding x constant is equal to the partial of n with respect to x holding y constant. We said that earlier. There it is again, right here. So now we're going to take those four equations and we're going to apply those principles. So if this is m, and this is n, and this is x, and this is y, then we can do that. So we come up with these four relations called the Maxwell relations, which help us to relate changes in property values with respect to another property value to some others. So this tells us how the change in temperature with respect to volume affects our change in pressure with respect to entropy, or temperature, pressure, and this is supposed to be lowercase v. I fixed that in the other one, but didn't get fixed in this one. So they all have these four terms: pressure, temperature, entropy, and specific volume, but it's just different ways of relating them together one to another. So depending on what you're able to measure in your system, like if you're able to measure the change in pressure and the change in temperature, then and the change in volume, then you can calculate the change in entropy. Or if you're able to measure volume and temperature here, then you can calculate this relationship between entropy and pressure. So it's really helpful, especially for calculating entropy changes. And why do we care about entropy? Why would we even want to calculate that? Those of us who care. If you don't care, then you just don't care. But why would we want to know how much the entropy is changing? What's it an indicator of?
The heat.
Wasted energy.
Wasted energy, potentially wasted energy, irreversibility, friction, heat losses, inefficiencies. Okay, so if we can calculate how much the entropy is changing and then run a system again with different configurations and see that we get a lower entropy change, then that's a positive, right? Because we're not wasting as much energy. Our system is more efficient. It's closer to being isotropic. On the note about systems being isentropic, actually, you guys have hopefully gotten your homework back. Problem 1, I think only one person actually calculated the entropy at state 2, 4, and 6 in the actual case. Okay, so when you have an isentropic efficiency, that means that you're going to have an actual enthalpy and an isentropic enthalpy, right? So you can use S to calculate your isentropic enthalpy. Well, if you have an isentropic efficiency, it means that your system is not actually isentropic, right? So entropy at state 1 is not actually equal to entropy at state 2, which means that you have to find the actual entropy in order to perform the rest of the calculations. So that's a very important concept that I want you guys to really think about and remember in future homeworks and quizzes, exams, whatever come up in the future, to know that not only do you have to calculate the actual enthalpy, which on problem 3, a lot of people miss that too, you would have to calculate an actual entropy, an actual temperature, an actual internal energy, an actual specific volume, that all of those quantities are going to be changing. The one thing that probably won't change is pressure. But all of these other quantities will change at the actual state. So, on that side note, let's do an example using the Maxwell relations to determine the entropy change with pressure for an ideal gas. So if we look back on this slide, so del S, del P with respect to T, whoa, wrong way. What does that match up with? Del S, del P holding T constant.
That bottom one?
Yep, this bottom one here. So this bottom relation is the one that we are going to use. Wrong way. So del S, del P with T being held constant is equal to a negative del V, del T, this is a lowercase v, with P being held constant. Okay, so we're given an equation, P times V minus B is equal to RT. If we want to find this, how do we use this equation and the relationship that we have between these two equations to give us anything useful? There's no entropy in this equation. How do we find a derivative, or a partial derivative of entropy with respect to pressure? What do you think?
Take the derivative of the volume with respect to temperature.
Yes, we have to do this side of the equation. So in order to do that, we need our equation in terms of specific volume. So PV minus PB is equal to RT. V is equal to RT plus PB over P. So if we take the partial derivative of this with respect to temperature, right? What do we get?
Just PB plus R over P.
R over,
No, PB plus R over P.
wait, hold on. RT plus, okay, so this is a negative. Okay, say again what you're saying. Who's saying that?
It doesn't matter.
Okay, so what is the derivative of negative RT over P with respect to temperature?
Negative R
Negative R
over P.
over P. Do you see that? So the derivative with respect to temperature of RT over P is equal to negative R over P. What's the derivative with respect to temperature of PB over P? The negative derivative. 0. So this is our answer for this equation. That the negative, there's too many negatives, whoa. I'm just glad the computer is actually letting me do the presentation. Okay, so negative R over B. Let's do another one. This time we're using del S, del V with respect to T. So where do we see that one? Del S, del V with respect to T. Which Maxwell relation is that? This one, number 3. So again, del S, del V with respect to T is equal to del P, del T with respect to V. That's the third Maxwell equation. So we want to now put this equation in terms of P so we can take the partial derivative of it. So P is equal to RT over V minus B. That's right. So del T of RT over V minus B is just equal to R over V minus B. Right? So it's just the derivative of T is 1, and then we multiply by R over V minus B, which is our constant. Okay, so the same equation, but depending on what we want to find, like we want to find how entropy is changing with pressure, or how entropy is changing with volume, then we're going to have a different relation that we look at.
What's the significance of B?
B is just a constant. Yeah, so there's just some gas that instead of being PV equals RT, it's P times V minus B, so there's like a correction factor in there. It's a not ideal gas, non-ideal gas, and so that's a common form of an equation of state, just to have B be a different constant depending on the gas. Okay, any other questions?
So those equations, like that top one, that's equal to the partial derivative equation for entropy versus pressure.
It's lovely. You think I'm crazy.
You're sadistic.
Okay, so now that we've gone through the Maxwell equations, we're going to take that third Maxwell equation. This is the third one. Del S del V with respect to T is equal to del P del T with respect to V. So when we're looking at phase change problems, we've already noticed and we've already found that pressure and temperature are dependent, right? So if you know the saturation pressure, you automatically know the saturation temperature for phase change problems only. So that's going from liquid to boiling, that's going from, we haven't looked at other regions of that diagram, but if we were to go from a solid to a liquid, or if we were going from a solid to a vapor, sublimation, then we could see similar trends that the saturation pressure and saturation temperature are going to be linked during any kind of a phase change problem, as long as we're changing between two phases. Okay, so what we can say is that del P, del T, during phase change, when we're looking at the saturation pressure, saturation temperature, that relationship between the two is going to be a constant. Okay, so we're calling this part of the equation a constant, which means that this part of the equation also has to be a constant. So now, instead of having a partial derivative, we can have a total derivative because of the link between those two variables. So we can rearrange these equations, so dp dt over ds dv, we can rearrange, yeah, so we take dv over to this side of the equation, and then we moved everything over there. So if we integrate along a saturation line, so from the fluid state to the gaseous state, to find this change in entropy, that it's the integral of this relationship between how the saturation pressure is related to the saturation temperature for that slope of the line times dV. So this would be our equation for that. So once we integrate, that Sg minus Sf is equal to that slope of the line between saturation pressure and temperature. And this could be for water, could be for refrigerant. That slope is going to be different depending on what fluid you're using. So then we can take this Vg minus Vf and just divide through over here. So we've just rearranged the equation again. That Sg minus Sf over Vg minus Vf is equal to that slope of the line for how pressure and temperature change during a phase change. Again, this is only during phase change. This is not everywhere. It's only under the dome or in the other areas where there's similar domes for solids and solid to vapor and things like that. Okay, when pressure is constant, we can take that second Gibbs equation for the change in enthalpy, and since pressure is constant, we know that enthalpy is equal to TdS, or dH is equal to TdS, which means that this ds, for this SFG, which is the difference between S sub G and S sub F, that's equal to a ds here, will be equal to this dH over T. So then we can just substitute that back into this equation, and we get what's called the Clapeyron equation. So this allows us to determine how much heat is required to undergo any phase change process based on that relationship between dP and dt, or the slope between the pressure and temperature during the saturation phase. Similarly, if we measure the amount of energy it takes for us to induce a phase change, or we somehow know that information, then we can figure out the relationship between the saturation pressure and saturation temperature. So depending on which one of those sides of the equation we know and can measure, then we can figure out the other one. So this is how a lot of the curves have been generated, because they were able to do these experiments. They were able to determine how much energy it required to induce phase change, and by doing so they can figure out the relationship between saturation pressure and saturation temperature. And so they run that experiment many times, and they were able to plot the points, and that's how they would get this dome. It's just by calculating all of these different distances until they figure out that relationship between pressure and temperature. Cool, right? So in general, for any phase change process, so whether it be from a solid to a liquid, solid to a vapor, vapor to a solid, gas to a liquid, liquid to a gas, then this relationship holds true, which is pretty fun. So let's just estimate, using this Clapeyron equation, how much energy it would take to vaporize steam at 300 kilopascals. So we're going to calculate it, and then we're going to compare it to the tabulated data that we have in the tables. Okay, so from the Clapeyron equation, HFG is equal to T times VFG dP dt set. Okay, now this problem is a little bit funny because we're going to the saturation tables to actually look up the values that we need, the delta V, the T, and that sort of thing. But in real life, you would have just done it experimentally. Okay. So we're going to use the saturation temperature at 300 kilopascals, VFG at 300 kilopascals, or V sub G minus V sub F, and then we're just going to look at some temperature and pressure range near those values. So we're going to go from 325 to 275 kilopascals, and Tsat 325 minus Tsat at 275. So if we go to the table, we look up those values. It's 133.52 degrees Celsius, but we have to convert it to Kelvin. 273.15 Kelvin is our TSAT. V sub G is 0.6058.82 minus 0.001073 meters cubed per kilogram. That's VFG. And then we have 325 minus 275 over this delta T. And because it's a delta T, we don't have to convert to Kelvin. We can convert both of them to Kelvin, but then the delta Kelvin cancels out. Degrees C. So the value that we calculate, H sub Fg, is equal to 2159.9 kilojoules per kilogram. Compared to actual, which is 2163.5 kilojoules per kilogram. So that's approximately 0.17% error.
Would that error go to zero as our pressure points, as our delta P, delta T went to zero?
Yeah, so the further apart they are, the greater the error. Because you're assuming it's linear, and it's not necessarily linear.
That's 0.17%.
Yes, yeah, 0.17%. It's not 17%. 0.17%. So very, very small error. So in an experiment, we would say, okay, I want to try to figure out the enthalpy of vaporization. So I'm going to see what the temperature is when at 300 kilopascals I start vaporizing. So you could hold the pressure constant and see what temperature it takes to where you start vaporizing something. Then you can say, okay, I'm going to measure the volume change as I go from a saturated liquid to a saturated vapor. That's easy enough to measure in a piston cylinder device. Then you can say, okay, I'm going to do the same thing at 325 and 275 kilopascals and see what how my temperature changes between those two pressures. So you could plug all of those numbers in and calculate how much energy it takes to vaporize something at a certain pressure. So this would allow you to perform an experimental analysis on your fluid. And if it was some unknown fluid that there wasn't a table for, it was some mixture you made in your kitchen and you wanted to know its enthalpy of vaporization, that's one way you could do it. So let's do another one where we have an unknown substance in a piston cylinder device, and we're going to try to figure out its boiling point temperature. So it's 2.5 kilograms of an unknown substance in the saturated vapor region. And we have it in a weighted piston cylinder device just so that we can maintain the pressure at 350 kilopascals. We know that we're removing 250 kilojoules of heat to go from a saturated vapor to a saturated liquid. So that would be like the HFG times the mass is equal to this 250 kilojoules. The volume of the cylinder decreases by 40 liters during the process, and the temperature remains constant at 10 degrees Celsius. So this is an experiment that we're performing and trying to determine the boiling point of a substance when the pressure is a different pressure than what we're currently using. Okay, so this is a good experiment to do in order to figure out that information. Okay, so again, this equation, dP dt, the Clapeyron equation, when we're holding it constant at saturation, is equal to HFG over T times VFG. What information are we given in the problem?
What temperature we're doing?
Okay, what temperature?
10 degrees Celsius.
Okay, 10 degrees Celsius, so 10 degrees Celsius, I'm just gonna go ahead and convert that to Kelvin, 283 Kelvin. That's our T. What else do we know?
We're given volume, but you would need to convert that
Okay.
to specific.
40 liters is what?
0.04 cubic meters.
0.04 meters cubed. And what else do we know?
H sub FG.
Okay, so we know H sub Fg times M. H sub Fg is equal to this 250 kilojoules divided by the mass is 2.5 kilograms. So we have 100 kilojoules per kilogram is our HFG. So we know HFG, we know our volume, we know our temperature. We can plug it into this equation to find how pressure and temperature are related. So HFG is 100 kilojoules per kilogram. T is 283 Kelvin. V sub Fg is equal to 0.04 meters cubed. So we find that the pressure changes with temperature, 8.829 kilopascals per Kelvin.
Wouldn't the 0.04 meters cubed have to be converted to meters cubed per kilogram as well?
You would need the specific volume.
Hold on. Kilojoules per kilogram is a kilopascal times a meter cubed. Kilojoules per kilopascal times a meter cubed. Do that. The units per count on that. I'll have to go back and double check, but because a kilojoule per kilogram is a kilopascal times a meter cubed is equal to 1 kilojoule per kilogram. No, it's a kilojoule. It's a kilojoule. Yeah, so we would have to divide this by also 2.5 kilograms. So divide by 2.5 kilograms. That messes everything up. Okay, so I'll rework this example and post it. But basically what you find here now is dP dt. dP dt, if we're assuming it's linear over that range, is equal to P2 minus P1 over T2 minus T1. So if you're trying to find the saturation temperature at a different pressure, so we know this is going to be the 450 kilopascals. We know this is going to be equal to 350 kilopascals. And this is going to be equal to that 283 Kelvin that we had from before. So we can find T2 is equal to T1 plus P2 minus P1 over dP dt. So this is the way that we could find what the saturation temperature would be at a different pressure if we wanted to know what that value was. So we perform an experiment at a specific pressure and temperature, measure the volume, determine how much energy is required in order to make that phase change occur. Then we can correlate that to another state and say, okay, this is how pressure is changing with temperature. So if instead I use this pressure, what temperature will be required? Does that make sense? Okay, so these Maxwell relations allow you to see the trends in how things change with respect to another property value, which then allows you to figure out what will happen in your experimental setup or in a design problem if you change a different variable, or if you work at a different state or different pressure. So it helps you see the trends in how your system changes, is basically what it's meant for. And And then in particular, entropy, which is a value that can't really be measured very easily, you measure other property values to see how it changes your entropy. So then you can say, okay, if I'm not operating at this temperature range, if I'm increasing it or decreasing it, how does that affect how much entropy is being generated? Or the entropy changes. Okay, so then the Clapeyron-Clausius equation is specific to the ideal gases. So if we then, knowing that V is equal to RT over P, and for an ideal gas, our V sub G is much bigger than VFG. So we're super far away from being a fluid. So our V sub G is huge. So we can say that the difference between the two is just approximately equal to V sub G. Does that means we're so far away from the dome and far above the dome that if we were to take V sub G minus V sub F, it's going to be approximately equal to V sub G because V sub F is so much smaller. So then we can say, well, we don't care, we don't need to know what V sub F is, we'll just assume it's whatever our volume is now. So then we can say V sub G is approximately equal to RT over P, or VFG is approximately equal to RT over P. And then just plug that into the equation. So now we can have it in terms of temperature and pressure and this R value. So this is specific to ideal gases only. So if we wanted to know how this variation of P stat happens with temperature for an ideal gas, then this is a special form of the Clapeyron equation that we can use that's only applicable to ideal gases or gases with very low pressures where their specific volume is approximately equal to V sub G, VFG. Okay. So this is all great stuff. I highly recommend you go through and read sections 11.1 through 11.3 and try to follow along again. Since this is new and foreign and different than what we've been doing up to this point, I think it will help you solidify it to see it more than once. And then if you look, I didn't do any of the examples that are in the text. If you go through those examples, I think it will help also. The ones I chose are different examples from other places so that you can have more examples to look at. So look at it, review, because on Tuesday, we're going to be doing more of this with other property values and other equations. So most of the differentiation is done, but we're still going to be using these types of equations to solve for unknown property values and relationships. Hey, so good luck. If you have any questions, send me an email and turn in your homework on Tuesday. Get started on it.